You know about derivatives and you know about inverse functions. So what about derivatives of inverse functions? Well, to start, let's pick a function that we know we can invert. I know that I can invert f of x equals x squared plus 1. You might want to pause here and invert it yourself just for practice. I'm going to start by switching variables. Y equals x squared plus 1. So to invert it, it's easy. X equals y squared plus 1. Only now we have to solve for y. Subtract 1 from each side. X minus 1 equals y squared. So take the square root. X minus 1 equals y. So now we have f minus 1 of x, the inverse of f of x, equals the square root of x minus 1. For convenience, I'm going to write that also as g of x, because g of x is easier to write and easier to read than f minus 1 of x. Here's a graph of it. Let's see what it looks like. There we go. Familiar parabola. You've probably seen something like this many times before. But there's actually a problem with this. We can't invert it because it fails what they call the horizontal line test. That is, you draw a horizontal line, and if it crosses more than once, and that means we have two different x values, this one and this one, that both correspond to the same y. And that's a problem because when you want to go backwards, now you give a y and you want a certain x. Well, this y has two different values of x, and we don't know which one to pick. So we need to restrict our function. We need to make it 1 to 1. That is, for every x, there's exactly one y. And we're going to do that by removing the left half. So we'll take off this part. We'll just erase this part. So what we're really saying is x greater than or equal to 0. And we'll take off the part we don't need. And here they are, both together. Here's x squared plus 1. Here's our square root of x minus 1. And you see the symmetry? You can even draw a line down the middle that shows that for every point over here, here's one, that's 1 comma 2, or we can say a comma b. There's another point over here on the inverse function that's just the same but opposite. In this case, it's 2 comma 1, or b comma a. And that's a property of inverse functions that you probably have seen before. So what about the derivative? Well, you know that the derivative's delta y over delta x. That is the change in y over the change in x. So we're going to need to find a change. And, you know, in the derivative, you find a secant line. Here, we'll go from this point. And let's draw a secant line. Can we get one? Ooh, just about right. There's our secant line. And let's give this point a name. We'll call it c comma d. So the derivative is delta y divided by delta x. Delta y, let's see, the y coordinates are d and b. So it's d minus b. And delta x, the x coordinates are a and c, so it's going to be c minus a. That's the slope of the line between the 2 points. And then we're going to perform a limit. We could squeeze a limit in here. C gets very close to a. That is, delta x becomes close to 0. Limit delta x approaches 0. Now, what does that look like on the inverse function? Well, there's also going to be a corresponding point, d comma c. And there will be a secant line between the 2 points. What's the slope of this line? It's going to be delta y over delta x, or delta g of x over delta x, because this one was delta f of x over delta x. And what's delta g of x? Well, that's, again, delta y over delta x. The y's, though, in this case are a and c. c minus a divided by delta x, and the x's are d and b, so d minus b. Do you notice what these slopes look like? Here's the slope for f of x, and here's the slope for g of x. They're reciprocals. That is, the slope of g of x is 1 over the slope of f of x. You might wonder about one more detail, the limit. Which limit do we want to use? If we want to be exactly the same, we'd have to say the limit as c approaches a. You know, because that's this one, c approaches a. But what if it's not the same? And what if we use d approaches b? Are they the same? Do they mean the same thing? If C gets close to A, does D get close to B? Well, under normal circumstances, yeah, as long as like the f of x isn't vertical or g of x isn't vertical, then as C gets close to A, then D will get close to B also. And that means that as D gets close to B over here, C will get close to A. So we can use the same limit, I think. C approaches A. We could also switch it up and say D approaches B, but they're going to be the same thing. So let's write these derivatives as equations. We just showed that g prime of B, is that right? X equals B equals 1 over f prime of A, right? F prime of A, here's our x coordinate, here's our x coordinate. So we've got two different x coordinates. Well, that makes sense. This point that's the same on the two functions isn't really the same. It's the switched x and y's, a comma b and b comma a. So if we used a over here, it makes sense we'd use b over here. So there we go. G prime of b equals 1 over f prime of a. Well, g prime of b, what is b? Oh yeah, b is f of a. So that's g prime of f of a equals 1 over f prime of a. Or, since a can really be any x, then we can write this as g prime of f of x equals 1 over f prime of x. But what if we want g prime of x? This is g prime of f of x, which is kind of a weird thing to have. G prime of x equals, let's get a little space down here. So here's our problem. We don't want g prime of f of x. Instead, we want g prime of x, which means we need to change this f of x into an x somehow. Fortunately, we're dealing with inverse functions, and that's exactly what they do. Kind of the definition of inverse functions is that f minus 1 of f of x equals, well, let's see, whatever f of x does, f minus 1 of x undoes. So that's going to leave us back with x. And that's what we want. We want to change this f of x into an x. So that means we need to do some kind of substitution, only this isn't quite right. I think we want the other way around, that is f of f minus 1 of x equals x, which is also true. I think we need a little more space. So let's substitute. We've got g prime of f of x equals 1 over f prime of x. And if we substitute x becoming f minus 1 of x, or, equals g of x, then we have g prime of f of g of x is 1 over f prime of g of x. So we substituted g of x into x, wherever that was. But this, of course, is f of g of x, which is x. And that means that 1 over f prime of g of x is g prime of x. Is that any better? Well, let's compare them. Let's scroll back up to our top. G prime of x equals 1 over f prime of g of x. That may seem a little strange, so let's check that answer with our example x squared plus 1. Let's go up here so we have a little space to work. Let's see, the derivative of x squared plus 1 is 2x, right? What's the derivative of square root of x minus 1, this g of x? It's a little messy. We're going to need the chain rule. So let's do a substitution. Let's say u equals x minus 1. Square root of u equals g of x. And the derivative is going to be g prime of x is 1/2 u to the minus 1/2 times du dx. Well, du dx, that's pretty easy. If u equals x minus 1, then du dx is just 1. So that means that g prime of x is 1 over 2 times the square root of x minus 1. Now, looking at these two derivatives and thinking one of them is the reciprocal of the other, your first reaction might be, what the heck? They don't look anything like each other. I see a 2 and an x, but nothing else. And you're right, because f prime of x and g prime of x may not be very much related. It's f prime of g of x and g prime of f of x that will help clear things up. So what's f prime of g of x? This would be 2 times the square root of x minus 1, and g prime of f of x should be 1 over 2 times, let's see, x squared plus 1 minus 1, which is 1 over, let's see, these cancel, you're left with square root of x squared, so 1 over 2x. Now I see some similarities. Let's see, we've got f prime of g of x and g prime of x. That's what we expected over here. G prime of x equals 1 over f prime of g of x, and g prime of f of x over here should be 1 over f prime of x. And look at that. It is. Is that the end? Did we do it? Well, let's see. First, we did this geometric argument saying that the derivatives should be the reciprocals. And then we did some math, and we found the derivative 2 different ways. We found it by substituting g of x into f prime of x and taking the reciprocal. And we used the inverse function and used the chain rule to find the derivative. And the answer is agreed. So yeah, we're done. If you want to try some others on your own, you might try the line f of x equals 5x minus 2. What is its inverse? What's the slope? Or you might try a more complex function, the rational function x divided by x squared minus 4. Now this one I like because it's not one-to-one. If you graph it, you'll see that it has 3 different segments, and you have to choose which one you're going to use. And you'll get different inverse functions depending on which one you pick. Have fun, and that's it for this video about the derivatives of inverse functions.